I'm really excited to be here. Thank you so much all for coming, and I'm really excited to talk about how Bayesian process models can help us understand big social science data. So let me just start with maybe stating the obvious. The technological advances have brought about a real change in social sciences because we can have now a large variety and amount of data on every individual. Just think about all the online activities people engage in, or think about the fact that most people now carry a smartphone with them during their everyday lives, which means that we can collect data passively, for example, on their GPS location from the smartphones. But it also means that we can actually reach individuals and we can ask them about their everyday life experiences. And today, I will be focusing on asking people, for example, about how they experience emotions during their everyday life. But we can ask them about their everyday life activities, how they slept. And people generally like tracking these things in their everyday lives. Like habit and mood trackers are really popular with the general public. So this is something people like engaging in. And another thing they like doing is wearing wearable health monitors, for example, Fitbit-like health monitors, to gather even more, not necessarily psychological state information on their everyday life, but physiological information, or information about their general activities, movements, and so on. So I guess what I want to say is that with this amount and variety of data, now we can move social science studies outside of laboratory settings, and we are able to capture everyday life experiences. And this capturing really means that we can concurrently assess various indicators of everyday life experience, so in real life context. Now, of course, the big question is how to learn from this data, how to gain valuable insights. And of course, the field of machine learning has provided us with great tools to explore associations, do predictions. But the type of models I would like to argue for today are the models where we are trying to use our theoretical background, existing theories, which can help us motivate how to explore the data. The theories that actually formulate what kind of underlying pathways, what kind of latent processes could have generated the data that we observe or we collect passively. And what I would like to focus on is also the fact that these models that we develop should be focused on within-person processes, because I believe that those are really important, and this kind of data should be analyzed together it should be analyzed in a way that we can look at within-person processes and between-person patterns together. Well, why is this important? I just want to give you a very small practical example. So are there any coffee drinkers here? I love coffee. Do you usually drink the same amount of coffee more or less every day? I usually take my 2 or 3 coffees every day, and I think most of us are like that. But there are some days when I just feel like, oh, I could have an extra coffee. Have you tried it? Have you just tried to increase your coffee intake during the day? What did you experience? Well, I'm a little bit in that kind of mood right now. I have increased my coffee intake, stimulate my brain. It's a little bit more fidgety, anxious, neurotic, so to say. And I think most people experience that when they increase the daily coffee intake, right? Like some people experience it less, and some people experience it much more, of course. So there is this association between daily coffee intake, but interestingly, if you look at between-person patterns, so you look at generally how neurotic or anxious people are on the trait level, it turns out that people who drink less coffee are generally more neurotic than people who drink more coffee. And there are several reasons for that. Maybe neurotic people just really focus on their health and they don't think coffee is helpful. So there are several ways to try to explore why this association is. But this is a typical association where the patterns across people, across the population of individuals are different from patterns within the individual. So the interesting models that I'm dealing with are trying to capture both of these processes at the same time. This means that there is something in social sciences we call multi-level modeling. So today I will be talking about multi-level Bayesian process modeling. And the process modeling aspect really comes from this approach that I described at the beginning, namely that we want to describe the theoretical underpinnings and pathways of the data generating process. And the Bayesian framework comes in because most often these models actually cannot be fit with the classical tools in the classical statistical framework. But I would also like to argue for actually using the Bayesian statistical framework as a really intuitive way of statistical inference. And the main example of this process model that I'm going to present today will be about how people's core affective states move around in an affect space. So this is the graphical picture here. So, but then I would like to start first with Bayesian methods. Like, why did I pick Bayesian methods? Why I think Bayesian methods are useful? The way I see Bayesian methods is that Bayesian statistical inference is that it's a very coherent way of, a very principled way of updating your state of knowledge. And this state of knowledge could represent, for example, if you have a very complex model, then what values, the parameters of that model can take, or it can represent the research hypothesis. So let's see an example on that you are actually thinking about the parameter, what values a parameter can take. You have some prior state of knowledge, and let's say here that it's really vague. Like, you know that the parameter can take values between 0 and 1, but you don't really have any idea which ones are more likely than the others. Then you get some data, and you describe the information in the data by a likelihood function. And what you do with the help of Bayesian is that you combine your prior state of knowledge together with the likelihood information from the data to get to a posterior state of knowledge that's actually described in terms of a posterior probability distribution on the likely parameter values. And you can see when you don't have a lot of prior state of knowledge, this will practically correspond to what you would learn from the likelihood function. Now, in other cases, of course, you have more prior information, and your data might say something that doesn't really align with your prior information, prior state of knowledge. Then your posterior state of knowledge will be a sort of like a compromise between the two. And if you really look at closely, you will see that maybe the most likely values of this parameter are actually a bit closer to what is likely under the likelihood function. And that's because Bayesian inference also takes into account the uncertainty between the prior state of knowledge and what comes in from a likelihood. And in this case in particular, you can see by the width of the distribution that there was more uncertainty in the prior than in the likelihood. Okay, so the way I can see that this is a very consistent way of updating your knowledge, introducing possibly prior knowledge into statistical inference. And this posterior distribution itself is really a very intuitive way to communicate the results towards people. So just think about, this is not that, but think about this posterior distribution as, for example, a posterior distribution for a standardized effect size. Then you can say that, okay, the probability that we have at least a medium-sized effect, so an effect that's like larger than 0.5 on a standardized effect scale, has, for example, around 90% of probability, and you get that probability by integrating over this posterior distribution above 0.5. Okay, so it's a very intuitive way, I think, to communicate the results, and also we are able, and the way we are able to get this kind of conclusion, this kind of inference, is really by sampling repeatedly from this posterior distribution. And most of the time, this happens most of the time that we have to draw posterior samples from the distribution. Not always, I will talk about that too. But once you have enough draws from the posterior distribution, so you do this iterative computation, you can actually derive any statistics of interest through Monte Carlo integration, through, for example, integrating over the values of this posterior distribution, getting the point estimate. And another thing, and the last and maybe the most important thing, or the one thing that I like the most about Bayesian inference, that it allows for sequential information accumulation. So it informs for a sequential, it allows for sequential updating in your knowledge. So you could use this posterior distribution as a prior when you have new data coming, and without recalculating your posterior and default data, you could just keep adding data and update your state of knowledge. And this applies, of course, for parameter estimates, but it also applies for much simple scenarios when you just simply have, for example, a research hypothesis against some null hypothesis. For example, here we had just one simple question. Our research hypothesis was that how much people feel love during their everyday life. Is that associated with how well they feel overall. Is that associated with their overall well-being? So it's a simple hypothesis testing for the existence of correlation or existence of no correlation. And you can see how the evidence accumulates, in this case, in favor of the alternative hypothesis. And here you can see the Bayes factor that expresses the evidence in favor of our research hypothesis against a null hypothesis of no association. So you can see that with every person, we are updating the evidence in favor of the research hypothesis, but we could have evidence in favor of the null hypothesis too, if that was the case in our data. And in this case, we actually found an extreme amount of evidence for this association to exist. And when it comes to the effect size, we also found that this is the posterior distribution of the correlation coefficient between the two. And you can see that the posterior distribution spikes around 0.6. So it's a relatively large effect in terms of effect size. Now, I hope that this was rather convincing, but you might know that not every statistician or not everyone does Bayesian inference. Do you know, is that surprising? Do you know why that is? Do you know about the criticisms of Bayesian statistics?
Well, and some people don't, it's too difficult to express the prior.
Yeah, the prior information, yeah. I think, yeah, it's a really good point. So it's really, people think it's non-scientific or too subjective to include prior information in statistical inference. So like, I would really like to touch on disadvantages in a way, or the criticism of Bayesian statistics. And this is a very interesting counter-argument, because for the Bayesians, the way they see the prior information is actually one of the greatest tools the Bayesian inference can give you. They see it as an analogy for like incremental scientific progress. This is how we make progress in science. We have some background knowledge, and we are building on that, and we are trying to update that incrementally. Besides, Bayesian priors can help you regularizing computational algorithms too, so it has some practical relevance too. But maybe to put it to look at an even bigger picture, I would like to quote two of the most famous Bayesian statisticians, maybe of current times, Andrew Gammon and Christian Robert, who called our attention that it's really interesting that people who criticize the Bayesian approach really strain on the specifications of the prior, which is more of like a net, and they swallow the specifications that belong to the likelihood. That is to say that if a models fail in general, or if something goes wrong, it's more often, it's the likelihood that is to blame, and the assumptions that go into the likelihood, rather than the assumptions that go into the different prior distributions of the parameters of the likelihood. So that means, of course, that the likelihood-based inference suffers from the same problems of misspecifications, because your likelihood is your assumption about the data generating process. Now, there is another problem, or another challenge for Bayesian inference that relates directly to ICS's mission, and that's the computational problems. Bayesian inference is computationally really expensive. And think about the kind of models or the kind of methods that I was trying to motivate in the beginning of the talk. Think about these real life studies when we have data from many people, and also different measurements taken many times a day for several days. And as I said in the beginning, we will want to fit relatively complex models of them. So then imagine if when you have to do this sampling-based algorithms, this sampling, iterative sampling, it can be really, really difficult, or can be really computationally expensive to fit these Bayesian models to big social science data. And I just want to step aside now and give you a personal account of how computationally expensive Bayesian inference is. So I did my PhD in Leuven, Belgium. It's a beautiful town with this medieval architecture. And I was also lucky enough to have my office in the ugliest building in town, which is great because you had the nice view on all the So I started my PhD more than 10 years ago. And I got a new top-notch state-of-the-art computer that looked like this, more or less. It's not a genuine picture, but I don't stand in you. It was top-notch because it was black. that was there, this time that gave it away. So it's not exactly my computer, but it looks something like that. So in a couple of months into the PhD, I was ready to fit my Bayesian models in a generic software package called Winbox, which had these built-in samplers. But what I noticed was that, okay, sometimes people say that, oh, I won't fit my model to data in Bayesian framework because it takes hours or days. And I usually argue that, yeah, but it's not usually hours that you actually have to actively work on fitting your model. It just happens in the background and you can just do other things. This is my usual argument, but I must say that more than 10 years ago, that didn't apply. So when I was fitting the model to the data, I could hardly do anything else on my computer. And when I complained, I got a key to our group's research lab, which I just really a lot of refurbished old computers, but at least I could let Winbox run there, and I could just start developing my own samplers, which I was hoping would be faster than Winbox, and I could be more computationally efficient. And well, that worked for a while, but a couple of years in, I realized that that's also not working perfectly. So I actually got access to the Flemish supercomputer syndrome. And this should be a genuine picture of that, the only one I could find online. So this is a supercomputer syndrome. It was still more than 10 years ago, so we are still at that timeline. And you can see that in those times, in a way, gentle petting or caressing of the supercomputers was still encouraged. If we look at ICS's current high-performance computing infrastructure, petting supercomputers was really discouraged. But these computers still do an amazing job, and I just couldn't do my job without them. Okay, but I must say also that hoping for bigger and better computers should not be the only way we deal with computational issues in Bayesian statistics. So now I would like to quickly summarize some of the ways that you can deal with actually the computational burden. First of all, you could stick with models that are relatively easy to, for which it's relatively easy to derive the posterior distribution, meaning that you could choose the prior and the likelihood in the form that when they combine together, they result in a posterior distribution that's actually analytically tractable, so it's easy to sample from, or it's easy to derive analytical properties. Unfortunately, this doesn't apply to the models that I'm interested in. Another very promising way is to approximate this posterior, for example, with variational proxies. But the problem is that this really needs to be tailored for every new model you are trying to put together. For tweaking the models, you have to retest these algorithms. So it has certain limitations, but I think it's still a very, very promising way of going. So what I do routinely in my work is really to do parallel computation. So to get samples from the posterior in a way that I run the algorithms embarrassingly parallel on different cores of the ACI cluster. And what we are also looking into is to do this embarrassingly parallel inference in a way that we actually divide the data into different subsets and then combine them together. So this is based on an algorithm, an embarrassingly parallel, synthetically exact algorithm from the machine learning group at Carnegie Mellon, where they developed a combination algorithm for the results that you get from every sub-posterior that you fit to subsets of the data. And as the number of samples from the posterior grow, you get an asymptotically exact approximation of the full posterior. So this is really promising, but the one approach I would like to talk a little bit more about now is really the one that I mentioned before, which I think is a great advantage of Bayesian inference, that you can do sequential updating, sequential inference. And this is great because in many of our projects now, we are really emphasizing on real-time inference. So this fits perfectly in a way with the idea of real-time inference. So to demonstrate the sequential information accumulation, the sequential updating in the Bayesian world, we analyze data from the Minecraft project, which is a large-scale web-based crowdsourcing project aimed at studying Alzheimer's dementia. And they have a couple of surveys online, and they ask people also to take some cognitive tests. They are hoping to gather data from 1 million people. At the time of the analysis, they already had like 60,000 participants taking this cognitive test and providing some background information. One of the tests is just a simple attention test. You have to push a button when a pink ball appears. So the data from every person you have from this test is just a repeated reaction time data, latencies between the signal and your response, and a model that was developed to model the underlying processes that generates this observed data. Actually, a model that has been used a lot in the literature is the later process model, linear approach to threshold with ergodic rate. Because the two parameters that this process has are a rate parameter that represents the information accumulation, and when it reaches a certain threshold, you're executing your response. So here is the latency distribution over trials. So this way we can get to only just, instead of only getting like a mean reaction time over the trials, for every person we are able to estimate their information accumulation rate and the threshold, which represents a kind of caution in the decision-making process. So what we did with this model first is we implemented a multi-level extension of it. So we assume this multi-level structure, a joint probability distribution on the top of all the person-specific parameters. And that also gave us an easier, like a straightforward way to regress the latent process model parameters on the predictors that were collected in the study. And for example, here I'm showing how, and this all done in one big Bayesian model, so that whatever uncertainty you have in the estimate of the latent process model parameter, like the information accumulation rate, is propagated into the estimates of the regression coefficients. Now, 1 million data points on repeated trials on this cognitive task might also represent computational bottlenecks, sometimes also just to read into the computer, but generally more if you want to fit this later process model. So what we did is that we tested a sequential inference algorithm for this data. We were updating the posterior distribution of the regression coefficients, participant batch by participant batch. So we batch participants, it worked out to be 549 participants. So we fit the model to these participants' data. To these participants' data, we got a posterior distribution of the regression coefficient, and then we use it as a prior for analyzing the data from the next batch of participants. And you can see as we add more data, the uncertainty in our regression coefficient decreases. One of the results we found was that with age information accumulation slowed down, but this is still an early stage result. Okay, so now instead of talking about the computational challenges, I would like to focus more about the advantages and show you an example of a multi-level process model that the Bayesian statistical framework actually enables us to think. So let's go back to our example on everyday life experiences, and that what we want to do in social sciences is really capture life as it's lived. We design ecological momentary assessment studies to do that. What we do in these studies is that we prompt people at random times to report on their experiences via some structured surveys that we put together. At random times means that we usually ask the participants when they wake up and when they go to sleep. Let's say we want to have 6 surveys deployed. We want to ask them 6 times to report on their experiences. Then we divide this time interval when they are awake into 6 equal length time intervals, and we assign a random prompt into each interval to make sure that we are actually randomly sampling about the experiences through the everyday life, and then the participants don't really expect, they don't really have an expectation when the survey will come. And in some studies, we also record physiological data with wearable devices. I will be talking about it too. So these ecological momentary assessment studies are really popular nowadays because of the obvious thing of increased ecological validity, because they allow for a frequent assessment. But if you think about how they decrease, for example, reporting biases, by actually asking about experiences as they occur in situ, not so that people don't have to think back on these experiences. If you set up a platform like this for assessment, you can use the same platform also to deploy interventions. For example, if you if the data shows that the person is experiencing increased levels of stress, you can easily deploy some small exercises to try to decrease stress levels. And alternatively, what we did in one of our studies was to try to increase people's daily well-being by deploying interventions in which we encourage them and in a way reminded them to be kind to other people, to perform some random acts of kindness, for example. So then you have the same platform for deploying the intervention and collecting the data, collecting the assessments as well. Now, the data you get from these self-reports, the kind of data you get is not really your ideal kind of data, though, because it's very it's a very unstructured data in the sense that all participants follow different data collection schedules. It's unequally spaced data. It's unbalanced. Every participant will have a different number of measurements. So not the kind of data that the typical conventional statistical tools can model properly. I would like to focus on one type of data we collected in these studies, and this is data on your emotional experiences, or as I will argue, on people's affect. Now, if I ask you how you feel right now, I believe that you would hopefully report maybe some excitement or happiness, or at least I'm hoping that you would be content. But I'm okay if you feel sleepy, it's after lunch, so that's. But I want to make a point for that. People usually report on their emotional experiences in this that we call discrete emotional categories. The interesting thing is, though, that when you look for evidence, physiological evidence or neural evidence for these discrete emotional categories, they don't really exist. So on the brain and body level, it looks like that there is something else, something more basic and continuous that exists, what we call core affect, which is a neurophysiological state composed of two dimensions. One is arousal, how awake and active you feel, and the other one is valence, or how unpleasant or pleasant you feel. And then most of these discrete emotions take place somewhere in this affect space. And of course, the actual emotional experience, although it is based on core affect, but it's constructed based on your past experience or based on your social context, for example, based on this theory of constructed emotions from Zita Oravecz. Now, measuring your core affect is actually very easy. I only have to ask you how pleasant and how active you feel right now at the moment. And we did ask this in a continuous scale in our study. This is my optimistic prediction for your current core affect. But I know that it's changing continuously over time. So I'm doing my best to try to maintain this level or not to let it drop too much. So let's see some real data. Let's see some participants from our first study, in which we enrolled 52 participants from Penn State into a 4-week-long experience something study. And what you see here is all data from 4 participants over the course of their study on core affect measures. One is valence and the other one is arousal. And if you just look at this data right now, I think the obvious thing to see is that people are rather different in their reported core affects. So one obvious thing is that their general state of core affect, or we can call this a baseline, seems to be different across individuals, but also the variation around the baseline is obviously, the fluctuations around it are obviously different. And this you might not see together easily, but maybe for some people they move together more closely, and for some people they might not correlate as closely. There is a theoretical framework called the DIN effect framework, which claims that individual differences in core affect experiences can be described in terms of 3 characteristics. It is based on literature review in studies related to affect. One is obviously the valence and the arousal baselines, or we can call them home bases or attractors to which your core affect system navigates back, to which your core affect system most often returns. There are, of course, fluctuations around these 2 baselines, and these are really due to the biocycle's social impacts in your everyday life that keep pushing your affect one way or another. but there is some regulation, some regulatory force in your core affect system, which either very strongly or not too strongly, but just gently pulling your core affect towards this attractor, towards this baseline. Now, what we would like to do is to model this core affect data, but in a way that we take into account this theoretically motivated characteristics of core affect. And for that, we borrowed a process from physics. It's called the Ornstein Uhlenbeck process, and it's a stochastic differential equation model-based process that was originally developed for modeling movements of particles suspended in water. So practically, if you think about this as being a pollen grain, and you put it in some liquid, then the pollen grain will exhibit some erratic movement as these small water molecules just bump into the pollen grain. But if you have a field of force, although it will be always deflected going away from this field of force, but it will also always return because it will be drawn towards this central attractor position. So this is some kind of analogy that we thought applies well to core affect as well. So the core, so let's say that this blue dot is your core affect system that's continuously impacted by your everyday life environment. So therefore it will show some variation around an attractor, around the baseline, but it will be always regulated back to a certain extent to some kind of baseline position. Now, if this is your core affect system, this is the theoretical representation of the process of how that changes over time. But of course, what we have as data are just some self-reports of core affect, which we will consider, of course, as noisy measures in core affect. So the Ornstein Uhlenbeck process can be used to model these latent changes, latent underlying trajectories in core affect. And we'll take into account that the observed data is perturbed by measurement noise. So the observed variation in the self-reported core affects can be decomposed into true core affect variation, inter-individual variation in the system, and noise variation due to measurement noise. Now, as I said, we are going to fit this Uhlenbeck process model for every person's core affect data. So for every person, we need to estimate the valence and the arousal baseline. Here the baseline is shown with this gray line, and here is just two different baselines. So this is what the difference between baselines look like. And then, of course, some people will have a lower level of fluctuations or variation around the baseline, and some other people will have higher. And the regulation will be also allowed to differ across people. And here is just some description or some visual representation of how a person with not much regulation would turn back to the baseline, would be drawn back to the baseline. You can see that for this person, it takes much longer when there is some impact that brings him or her away from the baseline to return. So the returns to the baseline are not as frequent, while this person gets the same amount of impact. So the reactivity or the inter-individual variation is the same across the two plots, but this person just returns to its core of the baseline much quicker. This, in other words, this person has a lot of emotional inertia in their core affect, and this person doesn't. This person regulates that really fast. Now, we will also model the relationship between the two core affect dimensions by estimating the contemporaneous association between them. So if you're higher in arousal, are you also higher in valence? And we will also estimate how changes in valence over time are associated with changes in arousal and vice versa. So some kind of cross-legged effect, but in continuous time. Now, all these person-specific parameters will be tied together by joint distributions. We will be doing, again, multi-level modeling. And this, again, is a straightforward way to introduce predictors into the calculations and try to see which predictors that are related to more like trait-level characteristics of the individual can predict these dynamic characteristics of everyday life core affect changes. We will also introduce time-varying predictors on the baseline to see that within individual are there some systematic variations based on time-varying predictors. And we are going to estimate all these parameters, 9 person-specific parameters, the multi-level parameters, the regression predictors, the variances, all in one big Bayesian model. Now, the goal of such exercise is really to try to learn about, to try to get a better understanding of these underlying pathways that tie together this fast moment-to-moment affect and your more slower timescale emotional experiences. And really the goal is to try to build some kind of causal models for emotional health, for example. And for that, we also introduce person-level predictors, which are actually centered on trying to measure your current emotional health. One is emotional well-being, so whether generally you have a steady, positive, stable mood. And the other one is how much role limitation you experience in your everyday life due to emotional problems. So, for example, everyone has ups and downs, but does that mean, for example, that you can't go on with your social activities? Do you have to withdraw from some of your everyday life tasks? Something like what we could see in depression, for example. So these are two subscales of the self-reported health questionnaire. So here are quickly some of the findings. We did find association between emotional well-being and core affect baseline. So it looks like that that higher emotional well-being means that people generally have higher levels of core affect. Variation in valence and pleasantness values was related to more role limitations in everyday life. And higher variation in arousal was related to lower emotional well-being. By this first study, we didn't find actually anything. We couldn't relate anything to the core affect regulation, which I must say for me, one of the most interesting parameter in this model, really how we regulate our emotions. But actually in previous studies done in Europe, actually, they found that what kind of emotion regulation strategies you choose in general can be connected with your core affect regulation, and more precisely, deploying habitually cognitive reappraiser. So trying to actually cognitively reinterpret some emotional impacts on your life, try to, for example, lessen the effect of the emotional impact, like trying to look at the bigger picture and so on. So that kind of, if you use that in your everyday life habitually, that's actually related to the lower level moment-to-moment core affect regulation. So we decided to try to replicate these findings and try to add to these findings and try to replicate findings from previous literature. So what we did was that we conducted another study, this time with a higher sample size with 160 Penn State undergrads. And this study, that was not the only purpose of the study. This was the study also in which we deployed these acts of kindness interventions and so on. So actually from the third week on, some people went through some interventions. That's why we decided just to make sure that, that these don't interfere with the results. We only looked at the first 2 weeks of the study to have comparable results to the previous studies. So just to remind you, our predictors are emotional well-being, role limitations due to emotional problems, and we are capturing emotion regulation strategies via how often people deploy cognitive reappraisal. And there is another strategy that's very often measured together with the cognitive reappraisal strategy, and that's like expressive suppression of emotions. Like try not showing your emotions, so try to change the behavior expression of emotions. We managed to replicate the results on higher core affect baselines being associated with emotional well-being, so we got the same results. And now role limitation was related not just to higher variation in valence, but in arousal too. So it looks like that higher variation seems to affect your everyday life functioning. And we did find what the previous study found, that core affect regulation was indeed related to more frequent deployment of cognitive reappraisal, and we didn't find any credible associations between emotion regulation and core affect regulation and emotion regulation by suppression. Which might make sense if you think, because suppression is really more about the expression of the emotion and not necessarily about the experiencing the emotion, the way cognitive reappraisal is trying to regulate the emotions. To also give you an insight into the amount of individual differences we saw in terms of how these core affect processes differ from individual to individual, this is a summary plot of all our Ornstein Uhlenbeck process model parameters, and every dot corresponds to a point estimate of an Ornstein Uhlenbeck parameter for one person in our sample. And the arousal estimates are in light blue and the valence estimates are in dark blue. So you can see that already in terms of baselines, so every estimate, every dot is one person's estimate, and this is like a smoothed distribution over the person's specific estimates. So you can see that the arousal base, that there are quite some individual differences in arousal baselines, maybe a bit more in valence. Valence also seems to be a little bit higher on average than arousal. However, when it comes to fluctuations around the baseline, valence, it seems to be less fluctuations in valence than, or generally speaking, most people would experience less fluctuation in their valence than in their arousal. When it comes to regulation, the between-person differences seems to be the same for both arousal and valence, and the individual differences here are also quite large. It's hard to see from the scale of this data, but like a person who has a 0.5 regulation could regulate back to their core affect baseline in half an hour, but people on this side of the scale would take around 5 or 6 hours to regulate their core affect back. It's hard to see the scale of the cross effects, but these were actually very small cross effects, so we didn't find a lot in terms of the cross effects, but we did find a relatively large contemporaneous correlation, so it did seem like that people who experience higher valence generally experience higher arousal too. We also allowed for arousal and valence baselines to change as a function on time of day in the diurnal cycle, and each line here corresponds to one person's estimated baseline over the course of the day. So we could see a clear quadratic pattern in arousal baselines and practically no difference in baselines with respect to valence. So this kind of real-time, real-life data collection, I believe when you model individual differences in the underlying pathways that generate the data, bringing us towards a general framework of personalized health. So it has some basic understanding of how short time scale and longer time scale processes connect and interact. And if you're able to better understand dynamic changes in core affect, you're practically in a better place also to develop, for example, in the moment, just-in-time interventions, and so on. So these person-specific patterns are very important for prediction. Now, but if you think about it, you can't really keep hoping that people will keep on reporting their core affect over time for weeks. So if you want to build a framework, if you want to have people, then you want to have like a prolonged intervention, the best would be if we could, in a way, predict these core affect states, these latent core affect states, from passively collected data, so that we don't burden the individual all the time with like 6 questions a day. So what we try to do is to tie core affect stat reports to passive measures. So in study 1, actually, half of our participants wore a wearable health monitor, the Infantica E4. And this is a research-grade health monitor that has 4 interesting sensors collecting physiological data. It has a photoplasmogram that can measure blood volume pulse, from which we can derive heart rate variability that's been tied to flight or fight response and so on. It has sensors that can measure electrodermal activity, galvanic skin response that's been tied with sympathetic nervous system activity, stress, anxiety in general, but also recently with attentional processing, for example. So this is one of the most interesting sensors that we get, or sensor information we get out, I believe, from this device. But we are also able to monitor activity, movements, and physical activity in general via the 3-axis accelerometer the device has, and it also has an infrared thermopile to measure skin temperature. Now, so So some of these physiological measures have been related to psychological variables, but most of these associations actually come from laboratory settings, where they have like very specific tasks to trigger some kind of emotional state, and then they see how responsive the physiological signals are, and so to derive this association. But what hasn't happened a lot is really to look at these physiological signals in everyday life. Like in everyday life, with these staff reports that I'm talking about, is there the same kind of association? So very easy thing we can do at first is just to check electrodermal activity levels like 10 minutes before the staff reports, and try to associate them with, try to predict arousal baselines, arousal and valence baselines from that. And this is these are our predictive trajectories for every person in the data set, for arousal and for valence. And what we found was that indeed electrodermal activity was a relatively good predictor of estimated of the arousal levels, but not of the valence levels, which is sort of encouraging. But when it comes to electrodermal activity, though, there's so much more going on than just looking at the level of electrodermal activity. So in another project, what we looked at is we just tried to do a classification study with random forest classifiers, where we try to predict low and high arousal states based on hundreds of features that we get from, that we extract from the electrodermal activity signals. And we do get 70–80% accuracy in predicting these high and low arousal values. But for me, one of the most interesting findings from this project was that actually the most important predictors, and here is the importance of the different features extracted from EDA for 3 people, and each line represents the importance of that predictor in the classification test. So what we saw was that for some people, the most important set of predictors were rather similar. For example, the change in different quantiles, different bottom quantiles, 30, 40, 50, 60% quantile, or the maximum of the EDA. But for other people, it was a completely different set of features that mattered. For example, this person, it was the count above the mean or count below the mean that contributed most to the prediction accuracy. Now, I think this kind of finding is great because it's actually just another evidence towards trying to build for personalized models of health, to try to tailor all these models for the individual. So we are trying to do that. We are trying to build these models and build a system for data collection with my colleagues Timothy Brick and James Mundy, and this is the WHERE IT project. So what we realized that, first of all, we need to just build a system that is able to collect and integrate this information for all the individuals. So we need to be able to build a system that can interface not just with the empathic ID4, we got that, but also with the commercial variables, for example, that people often use, like Fitbit, or even smartwatches have interesting sensors built in with them, like they can measure blood volume pulse, which is also a very interesting physiological indicator. So we need a system that can collect information from all these variables, from smartphones with different OSs to get GPS and so on, but to be also able to deploy the surveys that we actually want to use, for example, in the beginning to tweak our model for every individual. And so once we have like an integrated repository of all this data, then we are in a very good position to work out the analytic solutions with these personalized models and individualized models to explore further the associations or to describe theoretical processes, as I have talked about, and also to do predict vulnerable states and detect change points. So of course, we want to do this all in real time for developing the framework of efficient health informatics so that we are ready to intervene on vulnerable states. But just generally, if you think about such a framework, can really provide for a more general system for promoting and sustaining healthy, positive health behaviors. So we are going to deploy our system soon in our first pilot studies where the main topic we are focusing on is addiction, trying to break the addiction cycle. We will try to detect triggers for drug and alcohol cravings. And the system itself will be an app that the people will install. And I think it's a really nice way of helping people become healthier, because it's installing an app is a very low barrier for entry in these kind of programs. To conclude, I believe that we are ready for personalized health informatics, because we have the rich data, we have the sophisticated analytical tools, and we do have the fantastic computational resources, thanks for ICS. But what we're lagging behind right now is really the implementation to get this all together in a framework, test it, and tweak it bit better. And today I also wanted to make a case for individual-specific models that capture key processes and how these are important to deepen our understanding of these underlying systems. And Bayesian tools can fit these complex models. And I do think that Bayesian inference is also very intuitive. So it would be great to get to a level where from these models, we could actually communicate the results easily towards the individuals to enable this N of one kind of research, N of one kind of experiments, maybe, so that people could try to take their health into their own hands. So this technology-enabled methodology, just like EMA, as I showed you, is also great even if it comes without an intervention, because it generally just gives you a better understanding of yourself, of your emotional triggers. So sometimes they argue that the assessment itself is a kind of intervention, because it can be very helpful for individuals. Now, if we can put like on the top of that, like, so we can provide the individual with some easy to deploy strategies to, for example, give a fist bump if something is going well, or to just check in on the person. That it's almost like creating an AI partner on your journey towards a healthier life. So I would like to thank for my collaborators. I couldn't have done all this alone. Timothy Brigg, James Mundy, Amal Schütze, Kuala Lee, Brooke Cleveland, Liam Rand, Julie Wood, Seda Hasmati, Chelsea Murphy, Akim Bandikakoven, and many others. And for funding from the John Templeton Foundation, Social Science Research Institute for Cyberscience, and the College of Health and Human Development. And I would like to thank you for your attention, and if you have questions or comments.
Very amazing. Great work. Thank you. It's just, yeah, it's because it's different to, want to attack you reverse it to attack is that the arousal and the are they two outcome variables in a single model, or are they two outcomes variables for two separate models?
It's in one model.
In one model. So
yeah.
In one model, we model the two outcomes variables.
Yeah, it's a two-dimensional stochastic process model that can capture the effect of one variable on the other.
Okay. Got it. And another thing is that if we want to model the variation related to the time, for example, the change in one day. I'm just wondering if we assume there is a cyclic variation within, say, what kind of wire we can use.
Yeah, so this diurnal pattern, like indeed levels of arousal, this is, for example, a rather established pattern. So there's that we had here quadratic predictors on the baseline, and there was clearly this quadratic effect. And this is not the first time that this was established actually in the literature. So this comes up rather consistently. So this could be used, for example, as a prior information, like that you are expecting a quadratic term that's different from zero if you do inference again.
Okay.
Yeah.
Any other questions?
Yes.
So those arousal and those plots, there are like several lines. I had a hard time understanding what they were. So
Yeah, I'm looking. This is the time variable, right?
Yeah, so why are they doing so?
So these are the process model. So we had like 5 process model parameters, 3 for each dimension, the baseline, the intra-individual variation, and the regulation. So this is the baseline for every person changing as a function of the time of the day. And you can see that it's a varying intercept model, so each person has a different intercept. So each line is one person's predicted trajectory of baselines, how they change over the day. And we let the intercept differ for every person, the linear and the quadratic time effect coefficients differ for every person.
So it's a curve per person.
Yeah. It's just that they all look relatively similar. So it's not obvious, I think, that we are accounting for individual differences in the quadratic effects, for example, but we do. So.
Do you deal with, for missing data, do you deal with it just like in the conditional methods?
Could you repeat?
For missing data, how do you deal with the missing data?
Oh, missing data is a really interesting question. So we have, in this project, we assume that missing completely at random, because usually in the exit surveys, we ask people that if they missed data points, what was it due to? And most of the times they report something like, oh, maybe they shower and they didn't hear the signal. So we concluded that most likely it's not related to the actual thing we measure. However, I do think that this is really the next step, that it's very likely that, well, with these participants, right, who are undergrads, who are paid for participating, and who are motivated to reply, so like their payment depends on how many prompts, how many surveys they complete, and the survey's timeout. So they are very motivated to take the survey, right, every time. Now, later on, of course, it's very possible that we will have missing not at random, because if people feel really down, they are not going to care about like logging their core affect or answering these questions. So in other projects, I do think that actually modeling the missing data mechanism and actually trying to derive those states, those missing states, the missing self-reports is a really interesting question and could be made part of the state Bayesian model, because again, a nice thing with adding extensions in the Bayesian framework is for the missing data mechanism, you can build up a completely new probabilistic model and you can use that to impute the data that is missing. So in this one, to summarize, in this one, we just use missing completely at random, but I do think that that might not hold for future studies.
So for some of these very large scale data collection, like you mentioned earlier on, some project was aiming at 1 million responses.
Yeah.
How do people sort of, I mean, there's a missing data from, but also you don't have the detailed logs of, I mean, like data physiological responses, you know.
Yeah.
How do people sort of try to handle these kinds of problems? If you want to collect I mean, probably you have, time of the day, but you don't have other kinds of, maybe people thinking about it, naming the variables to them.
Yeah, so like, there's the thing that with that design, the questions you can answer is very limited.
Right, I mean, just to click the button, right?
And that's why we realized that, okay, but it's not that easy to integrate all this data together. Like it's like to be able to interface physiological data and do it all in one app that is also able to deploy surveys, that is also able to collect the testing information. This is something we really need, and it's not done in many studies because that will give us a complex picture, a complex understanding of what's really going on. And I do think that it's a very limited conclusions we can get from that study.
Yeah, I mean, I vaguely remember there was one NASA project I reviewed years ago that was proposing to collect a very large scale data by sending people like, Apple Watch or something, so that they can, when the person is doing the response, you can still collect it.
That would be great, and we are working towards that with the VRIT framework to be able to do that.
I think the personalized health informatics is a fantastic idea. Just a follow-up question on that is, when you integrate a large number of predictors from different individuals, how would your model handle the multi-collinearity? I mean, they're definitely highly correlated in terms of either psychological or behavioral or emotional data.
Yeah, so we can try to put some measurement model on the top of that, like some structure equation model, or we can try to do feature selection. So that's indeed like we have to do variable selection first before we can deal with that.
One more question?
I was just gonna ask, can you say again what the model was? I mean, you're probably doing this in R, imagine, is that the software?
Right now, yes, yeah.
It's not something people can just go do in Proc next, say you've got.
The Ornstein
multiple
model, no,
outcomes.
unfortunately.
Yeah, what is the name of the model again?
Ornstein Uhlenbeck process model.
Okay.
And I did develop graphical user interface based little standalone software to fit that model. But it's a bit more limited than the one I presented now, so it doesn't reward the correlation between the dimension. It's available on my website, but I developed it like 5 or 6 years ago, so now I think it's better. So because everything is hidden in the background, right? It's completely user interface based. So people don't really see what the model is about. They don't really see the underlying code or it's working with the MATLAB engine though, which is really nice because you can get that for free for your standalone little MATLAB programs. So that's the one for which I developed my own sampler, so it doesn't rely on JS. But I think that now, like I believe really strongly in open science, and that people should be able to see. And I would love if they understood also what's going on in the background. So that's why I'm moving towards R and actually like implementing these models in R. And I do have some code online.
Okay, as a token of appreciation for your talk today, we have a little gift for you. This
Thank you
is
so much.
ICS mark with logo printed in there.
Oh wow.
Please join me in thanking Dr. Oravecz. If you have additional questions, please come around. We have some cookies in the back, and you can ask Zita again for other information on the source code. Thank you.
Thank you.